Hello everyone, this is Group 1 CENG project assignment. I am Shlok Jain and I will be introducing you to our project. Our project is developed as a direct response to an issue which plagues society currently, an unhealthy over-reliance on oil as a means to meet a major fraction of energy needs, which is primarily spent on transportation. Though crude oil is an effective method to meet up energy requirements, overusage of oil has severe consequences on the environment. First, combustion of crude oil leads to the production of various deleterious products, such as nitrates and sulfates. Secondly, over-reliance on fossil fuels have led to a certain imbalance in the Earth's resources. And as fossil fuels are non-renewable and take over a million years to replenish, we need to find alternatives to reduce our over-reliance on oil. If I want to put this in simpler terms, then if we scale the Earth's life to 48 hours, then the human race came in 4 hours ago and the Industrial Revolution happened a minute ago. And in that 1 minute, we have destroyed 50% of our forests and used a majority of our resources. On a more economic and socially pertinent aspect, increasing global dependence on oil is poised to negatively affect the economies of nations involved whose primary source of energy is dependent on crude oil and its various byproducts. Decreasing amount of oil would create a scenario which would create a competition amongst buying nations. This would result in a larger monetary investment by these countries, the money which could actually could be spent better to keep a welfare state running. On a more historical scale, Simon Bromley, in a political dissertation, The International Politics of Oil, identifies the political ramifications of the dependence on oil. And well, if you know one thing, it is those who do not learn from history are doomed to repeat it. Slide 5, over to Preeti.
Hi, I'll be talking about the oil dependency of India. Currently, the oil dependence in India is taking a toll on the country's GDP. As seen in the pie chart, 95% of the energy consumed in India is derived from petroleum products. The value of India's crude oil imports rose rapidly between 2005 and 2009 due to increase in the consumption and the oil price. In 2009, 8% of the GDP was spent on oil imports. This was the largest import item on the balance of payment. This indicates that in the future, international oil price shocks could have significant impact on inflation expectations in India. Therefore, India is in a dire need to look for alternative sources of energy. Now I'll be talking about the environmental aspect of the problem. Residents of India's cities are no strangers to air pollution. For long, the country's capital, Delhi, has struggled with air pollution, majorly caused by the nearly 9 million vehicles that run on its roads every day. However, the situation has reached critical levels of late due to a complex mix of factors, including increased chemical residue blowing in from neighboring states where farmers set fire to straw in huge quantities. The PM10 and PM2.5 levels in the capital city are approximately 12 and 15 times over the WHO limit. The major causes of pollution in the country are motor vehicle emissions, exhaust of diesel engines, dust from construction, burning garbage, etc. The Delhi government is scrambling to provide respite by introducing various measures. However, these haven't really helped improve the situation in the country, and it is imperative to introduce new technologies that are green and sustainable. Over to Erica.
One of the leading renewable energies being used to combat oil dependency is solar power. However, what I'm going to be talking about is how existing solar cell technologies are unable to reach the highest efficiency possible. In fact, the theoretical maximum efficiency of solar cells itself is limited to just 33.7%. This is called the Shockley-Queisser efficiency limit. The Shockley-Queisser efficiency limit was calculated by William Shockley and Hans Joachim Kaiser in 1961. Basically, the limit means solar cells, specifically standard single p-n junction solar cells, highest possible efficiency is only 33.7%. In reality, most existing solar cells have a much lower efficiency. The record solar cell efficiency is held by University of New South Wales at only 25%. As seen in the graph on the right, current solar cell production efficiencies vary by the bandgap of semiconductor material used. For example, efficiency of a solar cell that's using gallium arsenide is higher than silicon. Also on the graph, it says blackbody limit. The Shockley-Queisser limit exists due to many effects. One of these effects is blackbody radiation. Any material that's not at absolute zero temperature emits electromagnetic radiation, and this means that as the temperature of the solar cell rises, heat loss increases, leading to a loss of energy and decrease in efficiency. Another effect is recombination. This is when a photon does not contribute to current. Hence, it also decreases efficiency. And lastly, only photons with energy higher than activation energy will contribute to current. Any energy above and beyond bandgap energy is also lost through heat. So where does 67% of energy loss go? 2% of energy is lost through recombination, 18% is photons passing through solar cells without effect, and 47% of it is converted to heat. This is where our solution comes in. Quantum dots. Quantum dots are capable of harvesting excess photon energy from photons higher than bandgap energy and turn it into electricity. Over to Sarah.
Thank you, Erica. I am Sarah, and I'll be talking about what quantum dots are. A quantum dot is a semiconductor crystal that encloses the motion of conduction band electrons, excitons, or valence band holes in all spatial directions. For those of you who don't know what excitons are exactly, excitons are bounded pairs of conduction band electrons and valence band holes. In current existing bulk material solar panels, the type of material being used fixates the band gap, which limits the absorption of hot electrons. But quantum dots have band gaps that are able to adjust across a wide range of energy levels simply by varying the size of the nanocrystals. Due to this stated property, quantum dots are the most effective and efficient material to use for multi-junction solar cells. Quantum dots haven't been around for long. They were first discovered by Alexei Ekimov in a glass matrix and in colloidal solutions and have been in use since the start of 1980s. The idea of using quantum dots to increase efficiency in solar panels was first noted by Burnham and Duggan 26 years ago. At the time, the science of quantum dots was still in its infancy due to the synthesis method being very complex. To make quantum dots, when the cadmium oleate sample reaches 225 degrees Celsius, we need to inject a trioctyl phosphine selenide solution. Then, small portions of this mixture should be withdrawn and placed in separate vials at room temperature to be quenched, and this maintains the small-sized quantum dots. The science behind how quantum dots works is actually pretty simple. In order for better understanding, I'm going to explain what band gaps are. The band gap is the energy difference between the top of the valence band and the bottom of the conduction band in insulators and semiconductors. In semiconductors, photons of energy less than the band gap of the semiconductor will not be absorbed, which means that the energy of the electron-hole pair produced by a photon is equal to the band gap energy. On the other hand, band gap of a quantum dot is size dependent and can be altered to produce a range of energies between the valence band and the conduction band. With decreasing nanocrystal size, the energy of optical transitions increases significantly. What I mean is when the size of the quantum dot is too small to be compared with the wavelength of the electron, the energy of the exciton increases as it is squeezed into this quantum dot. This phenomenon, known as the quantum confinement effect, occurs when the photogenerated electron and hole are confined by the quantum dot boundary. Therefore, as the size of a conductor particle reaches a nanoscale, the decrease in the confining dimension makes the energy levels discrete, and this increases or widens the band gap, which increases the band gap energy.
Since the band gap energy is inversely proportional to the square of radius of the quantum dot, as the energy gap increases, more energy is needed to be absorbed by the quantum dot. Research has shown that the optimum radius required for the maximum absorption is 27.5 nanometers. Therefore, optimization in quantum dot sizes is required for proper operation of quantum dot solar cells. Over to Genna.
Thank you, Kurti. And now I'll be comparing solar cells technology with existing ones. Compared to gasoline, electric, and hydrogen cars, solar cells ones are safer and more user-friendly than, say, hydrogen ones because hydrogen is very flammable. As for gasoline, diesel, and other types of fuel, solar energy is much more environmentally friendly, as cars run by solar power don't emit carbon monoxide or other harmful gases. Talking about electric cars, the main inconvenience is that they need recharging by the end of each battery cycle, while hybrid cars, say solar and electricity-powered ones, travel larger distances without charging, especially during daytime. Over to Kurti.
I'll be talking about the comparison between the typical solar cells and the quantum dot solar cells. So basically, the quantum dot solar cells have been found to have a number of advantages over the normal solar cells. To explain the advantages, we first need to know about the problems with the conventional solar cells. A significant part of the solar radiation is composed of visible and ultraviolet wavelength photons, which are not usually absorbed by the silicon solar cells. These photons excite electrons into higher levels of the conduction band, which heat up the solar cell and decrease its performance. The band gap of a quantum dot can be precisely controlled by its size, meaning that different sizes of quantum dots have different absorptions. It is therefore possible to synthesize quantum dots of various sizes that absorb most of the sun's spectrum, which is something that cannot be achieved using the conventional silicon solar cell fabrication. Over to Erica.
Now I'm going to talk about the actual model of our proposed solar car. Our proposed model will be similar in design to electric cars. There will be a lithium-ion battery underneath the car connected to the motor below the hood. Solar panels will be laid out over the roof of the car and the front. These panels will be connected to the motor using optical wires. Excess energy that is generated during the day will be stored within the lithium-ion battery to be used at night when there is no sunlight to drive the car forward. We believe this model is feasible with the use of enhanced solar cells because due to the quantum confinement effect, quantum dots are theoretically capable of achieving higher efficiency. Gasoline will not be needed if research into quantum dots continues to be successful and higher efficiency with solar cells are achieved. Obviously, the aesthetics of the proposed model car will be worked on after initial testing in order to appeal to consumers. Over to Sarah.
Capacitors could be another alternative for energy storage. Batteries discharge slower than capacitors because there is a latency associated with the chemical reaction of transferring the chemical energy in batteries into electrical energy. Capacitors store the electrical energy directly on their plates, so their discharging rates are directly related to the conduction capabilities of the capacitor's plates. So, if we need a high surge of power to run the car, for example, to accelerate, using a capacitor would be more beneficial as it can discharge electrical energy quicker than batteries. But if we're going to be driving long distances, batteries would be better to use than capacitors due to the battery's higher energy density.
In our model, we propose to install solar panels on the roof and the hood of the model car. To find out the number of solar panels that we can fit on the car, we took into consideration the dimensions of the model car and the surface area of our quantum dot solar cell. As an estimated value, we would be able to fit around 15,000 solar panels on the roof and the hood of the car. Over to Genna.
Now I'll briefly introduce manufacturing process of solar cells and their cost. The manufacturing of quantum dot solar cells is really complex, but I won't go into too much detail. Firstly, it is important to ensure the high quality of the base, which ideally should be the pure silicon. After the silicon sample is cut to the appropriate size, coating takes place. Coating consists of 3 layers: compact layer, active layer, and scattering layer. All of them mainly consist of titanium dioxide, which is fairly cheap. After that, actual quantum dot is placed on the photonode. Once quantum dot is deposited in the solar cell, it is time to coat it with a protective layer, which consists of zinc sulfate. Thus, with the current price of all the materials used for assembling a single solar cell will cost a bit more than 2 cents per unit, while for $1 it will be possible to manufacture nearly 50 cells. Thus, it will take about $300 to cover our model car with quantum dot solar cells.
There are some potential drawbacks of using quantum dot enhanced solar cells, but they can be improved. Quantum dots can blink and become invisible, as drawbacks on the quantum dot surface may lead to quantum yield deterioration. This implies that the ratio of emitted to absorbed energy is very low, and the low transmittance may stay undetectable or may require high sensitive detection systems. However, the surface defects, which are created by the recombination of electrons, can be tackled by employing a shell around the core, which would reduce the blinking effect.
There are also some drawbacks with the actual synthesis of quantum dots. Research has demonstrated that cadmium and other heavy metals are extremely toxic. Cadmium leaches into the cellular environment and results in cell death from damaged DNA. Despite this, we choose cadmium because a solution to the toxicity problem is that polymeric shells, the core protection of quantum dots, can considerably control the amount of metal ion leakage and hence control the toxicity. Over to Sarah.
The main drawback of lithium-ion cells and batteries is that these batteries require protection from being overcharged and being discharged too far. Furthermore, lithium batteries are relatively more expensive to manufacture due to the extra maintenance. Lithium-ion batteries are susceptible overheating and overcharging, and this may cause the battery to explode. Therefore, we need a cooling chamber for the battery, which will again increase the cost of production and bulk.
To sum up our presentation, quantum dots can prove to be a really promising solution to the problems that currently affect India. Quantum dot solar cells are cheap and highly efficient, and well, the benefits outweigh the cost. It's also noteworthy that perhaps is the best design alternative there is in the market. India happens to be one of the fastest developing countries, and a product like this would happen to be extremely profitable. Using quantum dot solar enhanced solar cells in India would reduce the infamous pollution levels and also improve the standard of living. Overall, this seems like an ideal idea, which only happens to lack execution. Thank you for your time.